In lecture 19, we will be continuing the discussion of making computer programs with decision making using if-else statements. We will discuss Boolean expressions whose output is always taken as either 1 or 0 or true or false. We will also discuss the logical operators such as and, or, and not operators. Then using these operators we can construct the compound conditions using if-else statements. We will also discuss the short circuiting when dealing with compound conditions, and we'll be trying to watch out for the logical errors when and which are actually not compile time or runtime errors when we will be dealing with the compound conditions. But first, before discussing all these topics, continuing from lecture 18, let's discuss the relays and their specifications, because to control appliances using microcontrollers, using relays is mandatory. Because if you want to control some appliances, the appliances are of 220 volts AC, and your microcontroller circuits actually run at 5 volts or maybe 3.3 volts. So I mean, relays, using relays is actually mandatory if you want to control a very big load of 220 volts or maybe 408 volts if it's a three-phase load with a simple microcontroller logic. Now, if you relays come in many shapes and sizes. There are electromechanical relays in which coil is energized by a control signal from a microcontroller or some logic circuit. That energized coil closes the contacts. When the coil is de-energized, the contacts open. There are also solid state relays which use power transistor to perform the same action. The basic premise or the basic purpose of relay is that it provides the isolation between the control circuit and the load circuit. The control circuit drives this coil, and this is the common point, and this common point is connected to this normally closed point when there is no power in this coil. But when we energize this coil, this common point is connected to this point which was normally open, so it connects to here when the coil is energized. I think I explained that. So let's take a look at this simple 5-volt relay which is commonly used with Arduino, and we have to understand the ratings of these relays. There are actually two sets of ratings. On the coil side, ratings we have on the voltage and current to energize the coil, and on the load side ratings we have what amount of current and at what voltage these contacts can actually withstand. So let's take a look at the Callside ratings. This is the features of a 5-pin 5-volt relay. By Callside rating, we have to take a look at what current is required and at what voltage to energize the coil. At the load side rating, we must know that what is the maximum current at what voltage is supported by these closing contacts. Now, looking at the relay specification, we see that the trigger voltage is 5 volt DC and the trigger current is 70 milliamps. These are Callside ratings. The maximum load current is 10 amperes for both of these cases, either at 250 volts alternating current or 30 volts DC. The operating time is 10 milliseconds to close the contacts, and the release time is 5 milliseconds to open the contacts, as obviously no switching action is performed in 0 time or instantaneously. Now, taking a look at the Arduino board specifications, and you can just search for Arduino Uno datasheet. That's a very simple, I think one of the very first Arduino boards. Now there are many other variations available. It says that let's look over here. Okay, it says that the DC current per IO pin is 40 milliamps. So, and in some cases, or maybe in some Arduino variants or some other boards, it could be 20 milliamps. The problem is that this 40 milliamp, or how can this 40 milliamp output pin drive the relay coil which required 70 milliamps to energize? So before answering this question, we must understand the concept of fan out and fan in. In a digital circuit, fan out means the maximum output. Let's take a look at some digital circuit before explaining that. Okay, it's a digital circuit. In a digital circuit, this fan out means the maximum output current per output pin. So if you see a fan out of 10 in the data sheet, it means that the single output can drive 10 inputs of the same logic family, such as CMOS or TTL, etc. You will learn about these logic families in your digital electronics course. Now suppose that I'm not saying specifically I'm discussing this 7-4 low power Schottky transistor. I'm not discussing this. Let's ignore what the numbers are. Let's suppose as an example that in this IC, I'm not saying it actually provides that, but I'm just saying suppose that this IC can provide 40 milliamps of current to maintain the true or logic 1 or high output. So if each of the inputs, so let's say I have this IC, let's say I'm talking about this IC. So let's say I have another IC over here, and this IC can provide about 40 milliamps of current to maintain the high output. Now let's say this IC requires 20 milliamps of current, and this IC also requires a 20 milliamps of current over here. So if I connect this point to this thing, so that means this output can drive 20 milliamps and 20 milliamps, and that means this IC can drive only 2 inputs at this time. If I connect another IC, if I connect IC, by IC means integrated circuit, and also requires 20 milliamps, so and I connect this point to here as well, so that I want to copy the inputs, the requirement is 60 milliamps. We have 20 milliamps here, 20 milliamps here, and 20 milliamps here, but this thing can only provide 40 milliamps. So if we try to connect another IC, either the output of this IC will fail to maintain the required voltage, or it might go into some illegal voltage range, which is neither high or nor low, or which we call a brownout, or it is also possible that this IC will just burn out. So if you want to drive multiple inputs whose current requirement is more than what this output can provide, you will be required to use some kind of a current buffer IC which maintains the input and output voltage, just copies the input voltage to output voltage, but increases the current capability to drive heavier or loads in higher quantities. The other term which we call a fan in, the first term was fan out, which was the maximum current drivability for output. Fan in is also actually important. It means the maximum sink current, or the maximum number of digital inputs that an input pin can accept. In some logical ICs, there are output pins and there are input pins. In Arduino, you can program that this pin would be an output pin or an input pin. The facility is actually there. So coming back to the original question, which was that how can a 40, let's look at that. That's how can this Arduino board with a DC current per IO pin of 40 milliamps can drive a relay coil which requires 70 milliamps to energize. Obviously it cannot do it directly, so either if you are using this relay directly with an Arduino board, you need some kind of a current buffer, or in this case let's take a look at the ready-made relay boards which are built for Arduinos, which are easily available from the markets. I mean, they look like this. We have 1 or 2 relays, and they might have 4 relays, or maybe and it's also possible that you have like 8 relays in a single board. So it depends on the requirement. One more thing I might want to add here is that if you're using analog circuits, and here we are talking essentially digital circuits, but if you're using analog circuits and you want to increase the current drivability of some output to drive some heavier loads, you will probably use something known as an emitter follower circuit. It's in transistor, it's an analog circuit. We are not going to discuss that, but you will see that in your some electronic design course. Now coming back to these relay boards, we have multiple relays, 1 or 2 or maybe 4, maybe 8, depending on requirement. If we look at the schematic or the circuit diagram of this relay board, let's say we have this relay board and we look at the circuit diagram over here. So let's take over here, this is it. I mean, this is the circuit diagram of this board over here. We notice that it has some kind of a diode over here, as well as some mysterious IC which has 4 pins, 2 on both sides, and it has another IC which 4 pins, 2 on this side and 2 on that side, and it has some input pins and the connectors for load side, as well as the signal over here which comes over here. So let's take a look at the schematic. And where's the schematic? Okay, so if we take a look here, then that IC is actually an optocoupler. Optocoupler is it's actually a 4-pin IC. We cannot see inside it, but the schematic is given, and by the schematic we can understand that there is a air gap isolation electrical isolation up to maybe 1000 volts. It depends on its specification. You might want to look up the data sheet. It has an LED inside. I'm not so sure what color LED is. Might be infrared. I'm not no idea. But it has an LED. We cannot see this LED. And the base of this transistor, is actually photosensitive. That means if this LED lights up, this transistor will become forward bias from base to emitter. When this LED is on here, this transistor will turn on. So the Arduino output is actually active low, which means that it's inverted logic. So to output high, we set the output to low, and when the output is set to low over here, this circuit is enabled. This is a 5 volts signal will come over here, and if we have a ground connection, output is set to low, which in Arduino means it's high. It's an inverted logic. You will understand because it's actually sinking current over here, so not actually supplying current. So it's just providing the ground path over here. So the 5 volt will forward this forward bias, or just turn on this LED as well as this LED. This LED is actually visible on the relay board. When this LED lights up, it will turn on this transistor, and this transistor will turn on this transistor. Therefore this 5 volt will come over here. This diode is reverse bias, so it's not going to run, and this coil is energized, and this energizing current will go from here to sync to ground. It will sync to ground, and that will close the contact. It will connect from pin 1 to pin 3. Now when the output here is set to high, that means it's 5 volts. This means that here is 5 volts, here is 5 volts. In this circuit there is no potential difference. 5 volts here, 5 volts here. There obviously there will be no current in this line, and this LED will turn off. This LED will also turn off, because since there is no potential difference or voltage difference, there will be no current in this wire, and this LED will turn off. This LED will that's a visible LED, but the LED inside this optocoupler will turn off. That will turn off this transistor, and that will turn off this transistor, and it will turn off the coil over here. I mean, this coil will no longer have the path to the ground, and it will be essentially disconnected, and this coil will the circuit is actually broken. So this coil from here to here, so this coil will de-energize using this diode, because it's actually collapsing the magnetic field. The voltage polarity will reverse, and this diode will become forward bias, and all the energy of this coil will circulate in this small circuit, and it will dissipate, and this contact, the 1 to 3 that was made before, will now be returning to its original position, and common pin of 1 will be connected to 2. Coming back to if else statement, we saw in the previous lecture that if this condition is true, then this statement will run, and if this condition is false, then this statement will never run. So that means that either you have some kind of a logical expression, or you can place some numerical values, even though that's not a very good idea, because if you know that this thing is never supposed to run, you can just write 0 over here, or any value other than 0 is taken as true. So I can write 1 over here, I can write like 100 over here, and this thing will still run. So I mean, any value other than any value other than 0 is taken as true. So this statement always runs, and this statement will never run. And you can also write true over here. I can just write true over here, and I can just write over false over here. So this thing, true and false, are implicitly defined in C++, and if you are running C language, I think you need to include something known as cst_bool.header file if you are running C language compiler. But C++ has these things as defined as implicitly these Boolean values, true and false, taken as 1 or 0. I can also write, if I want to write something like true, and here if I write false in capital letters, let's see if this thing runs. This thing says that going to report window over here, and it says that true is not declared in this scope. So I mean, true was defined as small letters, not in capital letters. So I can have another preprocessor directive, something known as defined. I can just write defined that whenever true, I mean this word here happens or is occurring, just replace it with this thing, this small true, and I can define another false. I mean this false with this false. I can also define some other constant if I want to, so I can just write define and pi. Let's take a look at the value of pi over here. The value of pi is 3.141, so I can just write 3.1415926535897, and it can go on and on. I think it's about 6 billion digits of pi has been known so far. So whenever this thing is mentioned anywhere in the code, due to this preprocessor directive or define, whenever I'm using pi, this thing will be replaced with this thing, and whenever I'm using these capital letters, I mean this thing would be replaced with this thing, and whenever I'm using this word for true, this thing would be replaced with this thing anywhere in the code. Let's run this thing, and now it says that this statement always runs, and this thing is okay because now we have defined the capital true as true. For further details of this define preprocessor directive, I would suggest you go to this website, c++.com/tutorial/preprocessor, and you can look at a very good definitions and the explanations of this preprocessor directives. But since we are at if-else statement, so this is not in the scope of this lecture. The next topic is logical operators, and we have three kinds of logical operators in C++. One is the AND operator. You have to use two ampersand signs, and you need to press Shift and 7 in that if you have 108 keyboard. And this is an OR operator. This OR operator, you have to put two vertical bars, and in my keyboard the vertical bar is right next to or above the backslash, so I need to press Shift and the backslash key. And this is the NOT operator. This is the exclamation mark, and if I press Shift 1, I can have this NOT operator over here. And to understand how these operators actually work, these are known as the logical operators, and they are used to form some compound condition. But first let's take a look at how these operators work. The AND operator is evaluates to true. AND operator evaluates to true only if both of the operands are true, otherwise it's false. AND operator is also known as the logical multiplication. The OR operator evaluates to true if any one of the condition is true, otherwise if both of the operands are false, then the OR operator is false. So let's make something known as a truth table. I have drawn the table beforehand, and in this truth table I'm going to discuss what is an AND operator. And our AND operator is defined by this double ampersand sign. So let's say we have a variable p and this have a variable q, and I want to do p and q. And p and q are essentially Boolean variables, so they can have true or false in there. So let's take a condition that if this thing is true and q is also true, T for true, then p and q would be true. So this is actually a easier way to understand is that the AND logical operator is a logical multiplication. So if you think that this thing is 1, then this thing is 1, then 1 into 1 is 1. Now if this thing is false, if any one of these conditions or both of these Boolean variables is false, then this thing would be, the output of this AND operation would be false. And let's say if this thing is true and this thing is false, the output would still be false, and this thing is false and this thing is false, the output is false. So the easier way to remember is that you can just treat 0 as false and true as 1. So 0 into 1 is 0, and this is essentially logical multiplication. Okay, so this thing is 1 and this thing is 0, so output would be 0, and 0 into 0 is obviously 0. The other operation is the OR operation, and the OR logical operation, and this is defined by two vertical bars. In some computers you might look something like this, depends on what kind of keyboard and what font you select. So let's say we have two operands, p and q, and they have the OR logical operation between them. So let's say we have true and true. So this OR is actually logical addition, and in this logical addition, and when both of these conditions or when one of those condition is true, so that the output would be 1. So if this thing is true, p is true and q is false, the output is still 1. If p is false and t is true, the output is still 1, or maybe true, I can just write that. And if when both of these operators are both of these operands are p and q are false, then the OR operation result is false. The last operation is the NOT operator. NOT operator is simple exclamation mark. So if we have p and we have and something like that, not p, so if p is true, not of p is false. If p is false, then the not of p is true. In numerical terms, I can just take this as t as 1 and false is 0, so 1 plus 0 is obviously 1, and false is 0 and t is 1, so 0 plus 1 is still 1, false is 0, false is 0, so the output 0 plus 0 is 0 for logical OR operation or the logical addition. 1 plus 1 is actually 2, but logically, I mean in Boolean the output is either 1 or 0, so this thing 1 plus 1 would be taken as true or just 1 only, and this thing can be taken as 1. If you just invert the logic, you get 0. If this thing is 0, if you invert it or the not, you've applied the not operator, you will get 1. So I'm talking about the digital inverter, not the inverter which you use in the power electronic devices which convert DC waveform to AC waveform. Not talking about that. Now since we know how these operations actually work, let's type an example of let's type over here. I've already saved these files and I've already included the IO stream and using namespace standard integer main void and return 0 with all the curly brackets. So I've already saved it, so it's not going to prompt me to save this file. Now I'm going to redo the program which we did in the previous lecture, and this program will try to find the minimum of 3 numbers as entered by the user, and we are going to use something known as the compound condition, because in if statement I can write a logical expression. So let's try to write this thing. Integer main void, I have written that, so I'm going to write just define 3 variables, integer n1, n2 and n3, and I'm going to see out the statement that enter 3 integers as we did in the previous lecture, and now I'm going to take the input, and the input operator, the first input entered by the user is assigned to n1, the second input is assigned to n2, and the third input as entered by the user separated by probably the enter key is assigned to n3. Now this thing is important, just pay attention over here. I'm going to write the compound condition over here. So I'm going to need to find the minimum of 3 numbers, right? So if n1 is less than or equal to n2, and watch out, I'm going to write and n1 is less than equal to n3. So just to make it more readable, I'm going to put some spaces over here. So this thing, now you take a look at this condition, that if n1 is less than n or equal to n2 and n1 is less than or equal to n3, that means that the cout, I can just write cout over here. Since in writing this one statement, no need for curly brackets over here. For this thing, the minimum is, and I'm going to write the value n1 over here, and that's it. Let's say that if the user enters 3 unique numbers, not the same number, so I can just delete this thing, and just to clarify the code, and I'm going to write enter 3 unique non-repeating integers, just to understand, because the focus of this code is how to write the compound condition. So that means that if n1 is less than n2 and n1 is less than n3 at the same time, if this condition is true and this condition is true, that means the output of this condition would be true, because I'm ending this thing with this thing. So that means that if this condition is true and this condition is true at the same time, the whole output of this Boolean output of this whole expression or the whole compound condition would be 1, and in that case this statement will run. So let's write another if statement. I'm saying that if n2 is less than n1, and I'm going to write and n2 is less than n3 at the same time. So I'm going to write cout, and I'm going to write the minimum is n2. So I'm going to, minimum is n2, and that's it. So that means that if n2 is the smaller of these 2 numbers, so I can write the compound condition. If this condition is true and at the same time this condition is true, the logical output of the whole expression would be 1, and this statement will run. And finally I can write the compound condition. If n3 is the smallest of the three numbers, so if n3 is less than n1, and at the same time n3 is less than n2, so that means I should see out that the minimum is n3. So let's run this thing. Enter three numbers. So I'm going to write, for example, 88 and 55 and 77. So it says the minimum is 55. Now let's see how it works. 88 was assigned to n1, 55 assigned to n2, and 77 is assigned to n3 because that was the third output. Now this thing is n1 is 88, so n1 is less than n2, 88 is less than 55. This thing is false. So if one of these condition is false, so obviously we know that in the AND operation, if any one of these conditions is false, so the output is false. Only if both of these conditions is true, the output is going to be true. So I do not even need to evaluate the next condition, because I'm going to explain that in the topic of short circuiting. But the computer or the compiler, when it sees that, or the program, when it sees that if one of these conditions is actually false and we have an AND operator, it simply does not even evaluate this thing. So but n1 is less than n3, 81 is less than n3, actually this thing is also false. So let's go to n2. I mean this condition, if this condition is false, this statement did not run. So let's going to the other. N2 is less than n1, 55 is less than n1, 88, that's true, and n2 is less than n3, 55 is less than 77. So this condition is true. That means this statement actually ran, and it says that the minimum is 55, which was n2. Now the third thing, n3 is less than n1, n3 is 77, n1 is 88. So this condition is true. Now it will evaluate this condition as well, because this thing is true, it might be true, it might be false. Here since it was false in the first place, it did not even evaluate the next condition. But let's see, n3 is less than n1, 77 is less than 88, that is true. So the output of this statement would be 1, and we are ANDing this with this logical statement. N3 is less than n2, so 77 is less than 55, that is false. So true and false would be false, so therefore the third statement did not run. To demonstrate the OR operator, let's write a very simple program of just asking the user something and just printing it, just to demonstrate that. So I'm just going to declare a character named answer, and I'm going to see out a statement, and I'm going to ask the user or the student that are you enrolled in some program or whatever. Okay, so I'm going to write y or n. User has to press the y or n over here. I'm not actually forcing the user to press y or n, I'm just giving the option. So I'm not even checking whether it's pressing any other character except y or n. So it's just, I'm going to take the input from the user, assign it to the character answer, and I'm going to write, pay attention over here, if answer equals to the character y, or answer equals to the character small y. So this thing, if this condition is true or this condition is true, so any one of these conditions is true, because we are using the OR operator, and we know that if any one of the conditions are true, the output is true. Only if both conditions are false, then the output is false. So here we are saying that either when this thing is true or this thing is true, the output would be true, even if the user did not press the if the user simply does not press the letter other y, except it's either a small y or capital Y, then this condition would be false, and this one would be also be false, and the output would not run. So I'm just going to write cout. I'm going to just press some or type some message, you are enrolled, and that's it. So and that's it. And else I can just write, if the if condition is not true, I can just write cout. I'm going to write you are not enrolled, and L. So let's run this thing and see what the output is here. Are you enrolled? So if I just press Y over here, it says you are enrolled, and if I run this code again, if I press capital Y over here, it just still says you are enrolled because this condition was true. So if this condition is true and we have an OR operator, the compiler or the program simply does not evaluate this condition, because it knows if any one of the condition is true, the other condition, whether it's true or false, it simply doesn't matter because we are using the OR operator over here. So if any one of the conditions are true, then it simply does not need to evaluate any other conditions. So let's try running some. Let's try N over here. It says you are not enrolled. Now in this case, answer equals N. N equals to Y. No, that is false. N equals to small y, that is also false. False or false, that is false. So this statement did not run. This statement actually ran. So even instead of pressing N, I can just have U over here. So I mean, you are not enrolled. I can just press any letter except Y, and we have the C out for you are not enrolled, because this condition is false and this condition is false. Compound conditions which use the AND operator over here or the OR operator will not even evaluate the second operand of the condition unless it's absolutely necessary, because if this thing is actually true, it's not needed to evaluate this thing, or in this case, if this condition is false, it's no need to evaluate the second condition, because if this thing is false, the output of this whole AND operation would be false. This is called something known as short circuiting, which I've explained a few moments earlier. And as we have seen these truth tables, the truth tables show that the condition P and Q will be false if P is false, and in this case there is no need to evaluate the Q or the second expression. Similarly, if P is true over here, so there is need to P, or in this scenario P or Q, there is no need to evaluate Q over here, because P or Q is going to be true. So in both cases, the value of the condition is known as soon as the first operand is evaluated. So even if you are using the AND operation, and if the first condition is true, only then the next condition is going to be evaluated. Or if this thing, and in the OR operation, if the first condition is false, only then the second condition is going to be evaluated, because the program does not know that whether the next condition is going to be true or not. So this short circuiting, let's write an example of let's write another example to demonstrate why this short circuiting actually is is actually helpful to avoid the program crashes. I'm just going to write a program which takes the input from the user, and we're just going to check whether the one number is divisible by another number. So obviously we're going to use the remainder operator. I've already saved the file as lecture194.cpp, and written all the program structure, so I suppose you should also write it beforehand. And let's declare two variables, integer n and d, n is the numerator and d is the denominator. So I'm going to check, I'm going to see out a statement, and I'm going to say enter two positive integers, because I'm going to use the remainder operator. So I'm going to take the input. The first input goes to n and the second input goes to d. So this is the assignment using the taking the input from the user. And now I'm going to write the compound statement or the compound condition in the if because we are going to write the logical expression over here. So I need to check whether d is not equal to 0, because we do not want the denominator to be 0, otherwise we have something known as a runtime error. So if d is not equal to 0 and remainder d equals 0. Okay, so we are going to write cout. I'm going to explain that in a moment. So cout d divides and n, that's it, n and l. Else we are going to write cout d does not divide and n, and that's it. So let's take a look how this program actually works. So if d is not equal to 0, so if we take two values, let's say 100, we press 100 for n and 5 for d. So d is not equal to 0, then we need to check whether it's actually divisible or not. Otherwise, if we do not check, we have some kind of an error over here. I'm going to demonstrate that. Let's run this code, and due to this antivirus software I have, now it will be okay. So enter two numbers. So let's say I press 306. So it says 6 divides 300. Yep, because 300 is the numerator and 6 is the denominator. So d is not equal to 0. So this condition evaluates to true because 6 is not equal to 0. And that is actually true. Yeah, 6 is not equal to 0. And 300 percentage d, 300 remainder 6 is actually 0. So I think this should be answer should be 50 if you divide it. So the remainder is obviously 0. Now let's run this code again. I mean this thing ran just fine. So I'm just going to run this code with another example. So F10 over here. Oh, sorry, it's the other program. Okay, so enter two positive numbers. I'm going to write 307, and it says 7 doesn't divide 300. So it first checked 7 is not equal to 0, and then it checked 300 percentage 7 is actually the remainder should be like 1 or 2, I don't know. So it's obviously 300 is not going to be divided by 7. The remainder is not going to be 0. So some non-zero value equals 0. This condition would be false. So this thing is true and this thing is false. The output would be false. So this statement did not run, and it says 7 doesn't divide 300. Now if I do something let's take another example, and let's write 300 0. So it says 0 doesn't divide 300. Now it prevented the program from crashing. So because if I say d percentage 0, so 0 is not equal to 0, this thing is false, and due to short circuiting it did not even evaluate this condition. So this short circuiting actually prevented the program from crashing, because when d is 0, the expression this expression they simply did not evaluate, because if one of the condition is false and you have an on or and operator, you do not need to evaluate the next condition. So if I remove this check, so let's say I remove this check and I say if n percentage 0, and then yeah, d divides 0, and just run this code again. Let's run this code. Enter two positive numbers. I'm going to press 300 and 0, and the program actually, it says lecture 19.4.exe has stopped working, and it crashed the program. To prevent this thing from happening, what we need to do is we need to use something known as this short circuiting, because I'm going to press, I need to check first this thing should this thing is not equal to 0. Otherwise we have the divide by 0 problem over here. Just to summarize what we did the relay ratings and the Boolean expressions, and we saw that if this thing is if you just write any value other than 0, this thing is going to be true. So if you want just to run some statement, you don't even need to write this thing, just to explain that if runs if it finds 1 or any value other than 0 in its round brackets. So and we also saw how logical operators work, and we also saw how to make compound conditions using these logical operators, and we took the input from the user, and we did these we explained the concept of the short circuiting. The logical errors when dealing with compound conditions is going to be explained in lecture number 20.